Well, in the first video on one-point compactification, so we have defined local compactness and we have given some examples of locally compact topological spaces. Then also we have given some non-examples, Q and R omega. These are not locally compact topological spaces. Then we have defined what are nice topological spaces. Those are metrizable spaces and compact Hausdorff spaces. Then we have asked the following question. Suppose X is not nice, that is X is not metrizable space, nor it is compact and Hausdorff. Then the question is, can X be a subspace of a nice space? That is, does there exist a nice space such that X is homeomorphic to a subspace of the nice space? And note that a subspace of a metrizable space also metrizable, because a subspace of a metric space is again a metric space. Therefore, the refined question is, under what conditions X is homeomorphic to a subspace of a compact and Hausdorff space? That is, under what conditions there exists an embedding f from X to Y, where Y is a compact and Hausdorff space. The theorem below answers the question. It says that a topological space X is compact and Hausdorff if and only if there exists a topological space Y such that X is a subspace of Y. The complement of X in Y is singleton set. That is, the number of elements in Y minus X is equal to 1. And the third condition is Y is compact and Hausdorff. Furthermore, if Y and Y prime are two topological spaces satisfying these three conditions, then there exists a homeomorphism from F from Y to Y prime such that F is identity when it is restricted on the subspace X. So in this video we prove this theorem. There are three parts in the proof of the theorem. Firstly, the forward direction. Here our assumption is X is locally compact and Hausdorff. We have to show that there exists a topological space Y that satisfies conditions 1 to 3. That is, X is subspace of Y. The complement of X in Y is singleton, and Y is compact and Hausdorff. The second part, that is the converse part. Here our assumption is, suppose there exists a space Y satisfying condition 1 to 3, that is X is subspace of Y, the number of elements in Y minus X is equal to 1, and Y is compact and Hausdorff. Then we have to show that X is locally compact and Hausdorff. Finally, we have to show uniqueness. That is, suppose there exist two such topological spaces, y and y prime. Then by condition 2, that is for y, the complement y minus x has only one element, so we assume that y minus x, that is equal to singleton set P, and similarly we assume y prime minus x, this is equal to singleton set Q. Then we have to show that the map f from y to y prime defined by f of x equal to x for all x in the subspace X, that is f is identity on the subspace X, and f of P equal to Q. Okay, so that the map f is bijective. Okay, so we have to show that this map f is a homeomorphism. First we prove uniqueness, that is the third part. So we have to show that f is open map. Then by symmetry it implies that f is homeomorphism. So by the definition of the map f, one can see that f is bijective map. Now if you can show that f is open map, then by similar argument but interchanging the role of y and y prime, you can see that f inverse of f, that is also open map, and when f is open map, then f inverse is continuous, and when f inverse is open map, then f is continuous. Okay, so that then symmetry will imply f is homeomorphism. Therefore it is enough to show that f is open map. Now suppose u is open subset of y, therefore we have to show that f of u, that is open in the codomain y prime. Now we have two cases. Case 1, p does not belong to u, and p belongs to u. So when p does not belong to u, then one can see that u is actually subset of x. Okay, and on x f is identity, therefore f of u equal to u. Now u is open in y, and by assumption this u is open in y, so u is open in y and x is open in y. Therefore u intersection with x, that is actually equal to x, that is open in, so u intersection with x, that is equal to u, because u is subset of x. Okay, u is subset of x, so therefore that is intersection is open in x with subspace topology. So therefore u is open in the subspace x. Okay, on the other hand, now we have, from here we have u is open in x and x is open in y prime. Okay, these two conditions together imply that u is open in y prime. So well, say y and y prime, they are compact and Hausdorff topological spaces. So one point set that is one point singleton set P is closed in y, so the complement that is equal to x. X is open in y. Similarly, x is open in y prime. So let us review case 1. So when P does not belong to U, then we have U is actually subset of X, okay, and U subset of X. Then we have shown that U actually open subset of X, and on the other hand, U is open subset of X, and X is open subset of Y prime. Therefore, U is open subset of Y prime, and that is equal to f of U. Therefore, we have shown that U is open implies f of U is open in Y prime when P does not belong to U. Now in case 2, suppose P belong to U, okay, then we define C equal to Y minus U. So U is open in Y, so Y minus U, that is equal to U complement, okay. Therefore, this is closed. Complement of open set is closed. So C equal to Y minus U, that is closed in Y, and Y is compact. So closed subset of a compact set is again compact. So therefore we have C is compact. Now C is actually contained in X, okay, because C is subset of Y, C does not contain P, therefore C is subset of X, and therefore C is also compact subset of X, because C is compact subset of Y and C is subset of X, therefore C is compact subset of X. Because X is subspace of Y prime, C is also compact subspace of Y prime also, okay. So C is compact subspace of Y prime, that is, and Y prime is Hausdorff, so we have C is closed. And what is C complement in Y prime? That is equal to exactly f of U. F of U equal to Y prime minus C, and C is closed in Y prime, therefore the complement of C in Y prime, that is open, therefore f of U is open. So our conclusion is f is homeomorphism, because f is open map by symmetry, we have f is homeomorphism. So uniqueness part is done. Now we prove the forward direction, that is, here our assumption is okay. Let us recall our assumption. Yeah, this is the forward direction. Assume that X is locally compact Hausdorff space. So we have to show the existence of a topological space Y that satisfies conditions 1 to 3. Okay. So here the proof is by construction of a topological space Y. So we define Y equal to X union with infinity. So infinity, this is an object, okay, this is an object that is not a member of X. So this is the hint that our space Y should have one more element than X, that is Y minus X should be singleton. So this is the hint, Y should be X union with some extra point, some extra single point. So we define Y equal to X union with infinity, okay. So set y is y equal to x union with infinity. Okay, so here infinity is an object that is not a member of x. Instead of infinity, you may use another symbol, for example p. Now we define topology on y. So by describing the open sets in y, therefore the open sets in y are following. There are two types of open sets in y. Type 1, that is equal to that is the set tau 1 that is equal to u such that u open subset of x. Okay, u such that u is open in x, that is u belongs to tau x. This is exactly equal to tau 1 equal to tau x. Tau x is the topology on x. This is the set of all open subsets of the given locally compact and Hausdorff space X. Okay, so this is because we have to get the first condition, X is subspace of Y. So of course, so open subsets of X are open in Y also. Okay, and type 2. So this is the set tau 2 equal to u, where u equal to y minus c, where c is some compact subset of x. So complement of compact subsets of x, then complement in y. So this is type 2 open subsets of y, and we defined tau y that is equal to tau 1 union with tau 2. Now so now we claim that tau y, this is a topology on y. Okay, now many things we have to check here. Firstly, we have to check tau y is topology on y. Well, the first condition to check is empty set and whole space y, these are open. Okay, now see, empty set is in tau 1 and tau y equal to tau 1 union with tau 2. So empty set is also in tau y. So empty set in tau y, this is open of type 1 because empty set is in tau 1. Okay, so empty set is open in y. Now we have to show that y in tau y. Okay, so basically see, empty set is compact. So so here we consider C equal to empty set, and that is compact subset of X, and y minus empty set, that is equal to y. So so full set y is in tau 2. So full set, this is open set of type 2. The second condition is we have to show that tau y is closed under finite intersection. Basically, we have to show that for u1 and u2 in tau y, we have to show that tau u1 union with u2 in tau y. Now there are three cases. In the first case, if u1 and u2 both are open of type 1, that is u1 and u2, they both are in tau 1, then their intersection is also in tau 1, because tau 1 is closed under finite intersection. because tau 1 is topology on X. Okay, so if U1 and U2 both are open of type 1, then we have U1 intersection with U2 in tau 1. Now if U1 and U2 both are open of type 2, then Ui equal to y minus Ci for I equal to 1 to 2, where Ci, these are compact subset of, so these are compact subsets of X. Now U1 intersection with U2 equal to, so U1 equal to y minus C1 and U2 equal to y minus C2. If you replace U1 and U2 by y minus C1 and y minus C2 respectively, then we have U1 intersection with U2 equal to y minus C1 intersection with y minus C2, and that is equal to y minus C1 in union with C2. And C1 and C2, they are compact subsets of X, so their union is also compact subset of X. Okay, so y minus compact subsets, some compact subset C1 union C2 of X, that is open of type 2, that is in tau 2. Okay, now if U1 in tau 1 and U2 in tau 2, that is U1 is open of type 1 and U2 is open of type 2, then for U2 we have some compact subset C2 of X such that U2 equal to y minus C2. Now U1 intersection with U2 equal to U1 intersection with, now you replace U2 by y minus C2, then we have U1 intersection with y minus C2, and that is equal to U1 intersection with x minus C2. Okay, and x minus C2, this is open of type 1 because C2 is compact in X, therefore closed in X, and the complement x minus C2 is open in X. So this is in tau 1, so therefore x minus C2, this is open of type 1. So open of type 1 intersection with open subset of type 1, that is again open subset of type 1, so that is in tau 1. Okay, so therefore so we have proved that tau y is closed under finite intersection. Now the third condition to prove that tau y is topology on Y, we have to prove tau y is closed under arbitrary union. Basically here the arguments are basically same. So consider a collection of open subsets U alpha, where alpha belongs to some lambda. If the collection U alpha belongs to lambda is of type 1 open sets, then the union U alpha, where alpha belongs to lambda, this is equal to U, this is open of type 1. And in case 2, if we have U alpha collection of open sets of type 2, then U alpha equal, so here we use different index sets, so beta. So suppose yeah y minus c beta, this is beta belongs to omega. Okay, if this is a collection of open subsets of type 2, then its union is equal to y minus intersection of c beta. Beta belongs to omega, and note that this is compact. Okay, this is compact subset of X, because c beta is compact for every beta. So c beta is closed for every beta, and arbitrary intersection of closed sets in a topological space is again closed, and so therefore this intersection is closed. Okay, now this closed set is subset of compact set. So for every compact set C beta, this intersection is subset of that compact set C beta. Therefore this is compact. Okay, so y minus compact set intersection C beta beta belongs to omega. This is open of type 2. Okay, this is C equal to intersection C beta. Beta belongs to omega. C is compact in X. So y minus C, this is open of type 2. Now if we have a mixed collection of open subsets of open subsets of Y, that is mixed collection of elements from tau y. So this is the first collection, open subsets of type 1. This is second collection. So second collection of open sets of type 2. Then union of u alpha, this is u. Okay, this is u, open subset, again open subset of type 1, and here we have seen that y minus c beta equal to y minus c. This is open subset of type 2. So this union u alpha belongs to lambda, this is equal to u, and this union equal to y minus c. So this left hand side equal to u union y minus c, and this is equal to y minus c prime, where c prime equal to c minus u. C is, so again c is compact, u is open, so c minus u, this is closed. Okay, closed minus open set is closed, and this is c prime is closed subset of compact sets, so c prime is also compact. Okay, so therefore we have proved that tau y is topology on Y. Now we have to prove, we have to show that this topological space Y satisfies condition 1 to 3. First condition is X is subspace of Y. Okay, so first condition is X is subspace of Y. So basically we have to show that if U is open in Y, then U intersection X is open in X. So if U is open in Y, means U belongs to tau Y, that is U either belongs to tau 1 or U belongs to tau 2. If U belongs to tau 1, then we have U intersection X equal to U, that is open in X. This is trivial. And now if U is open of type 2, then U intersection with X equal to, now U equal to Y minus some compact set C, because Y is of type 2. So this is replace U by Y minus some compact set C in X. So this is equal to Y minus C intersection with X, that is equal to X minus C. Okay, so X intersection Y, that is equal to X, and C intersection X equal to C, because C is subset of X. C is compact subset of X. Okay, so X minus C, so C is compact subset of X. So C is closed in X minus C, that is equal to C complement, and C is closed, so complement is open. So this is open. Okay, this is open in X. And conversely, if U is open in X, then U is open in Y of type 1, so U intersection Y equal to U. That's it. So converse is trivial. Now we have to prove that. So this is the first condition of the theorem. So, and condition 2. So recall that here we have condition 2. So by construction we have y minus x equal to infinity. So it has only one element in the complement of x in y. Now we have to check the third condition, that is we have to show that y is compact and Hausdorff. Okay, so basically, once we prove y is compact and Hausdorff, then we will be done. So first we prove that y is compact. So to show that y is compact, what we have to show, that for a given arbitrary open cover A of y, we have to show that A admits a finite subcover. Okay, so infinity is an element of y and A is open cover of y. Therefore there exists some element u naught in A that contains infinity. Okay, and by construction, if u naught contains infinity, then u naught should be open set of type 2. Therefore u naught equal to y minus c naught, where c naught is compact subset of the subspace X. Now we construct the collection A prime, which is equal to U intersection with X, where U belongs to A minus the singleton set U naught. Okay, then it is easy to see that A prime is an open cover of C naught, and C naught is compact in A, therefore it admits a finite subcover, let's say U1 intersection with X and so on, UN intersection with X. This is finite subcollection of A prime. This is finite subcollection of A prime cover of C naught, because C naught is compact in X, and this is collection of open subsets in X, which is a covering of C naught. Okay, and this is your finite subcover. Then it is easy to see that the collection U naught, U1 and so on UN, this is a finite subcollection of A, which is a finite covering of the topological space Y, therefore Y is compact. Now we show that Y is Hausdorff. Let X not equal to Y to distinct elements in the topological space Y. So now we have two cases. If X and Y, they both are in the subspace X, then we have two disjoint open sets U and V of type 1 containing X and Y respectively. So, and they are disjoint because X is Hausdorff. So therefore if X comma Y, they are in the subspace X, then we can find two disjoint open subsets of type 1 containing X and Y. Now in the second case, if one of them is infinity, suppose Y is infinity, then by local, so here we use local compactness of X. So by local compactness of X, see X in little x is a point in X, so local compactness property says that there exists some compact subset denoted by Cx, compact subset Cx in X that contains an open neighborhood of X. Let us denote that open neighborhood by Ux, okay, such that X belongs to Ux contained in Cx, and of course Ux closure is also Cx, is in Cx because this is Cx is closed subset of X because it is compact in X, and if Ux subset of Cx, then Ux closure is also a subset of Cx, okay, because Ux closure that is smallest closed subset of X containing Ux, okay. So fine. Now you can see that Ux and the complement of Cx in Y, they are disjoint. Ux and Y minus Cx, these are disjoint open sets in Y, and Ux contains X and Y minus Cx contains infinity, and this is open set of type 2. So when X belongs to X and Y equal to infinity, okay, two distinct points in Y, then we have an open subset of Y of type 1, that is Ux, and an open subset of type 2 Y minus Cx, okay, containing infinity, containing X and infinity respectively, and they are disjoint, okay. Therefore Y is Hausdorff. So this completes the proof of forward direction. Now to prove the reverse direction, so therefore that is the reverse direction is here our assumption is so here our assumption is suppose there exists a topological space Y satisfying condition 1 to 3. So we have to show that X is locally compact and Hausdorff. So Hausdorffness is very simple because see X is subspace of Y, Y is Hausdorff, and it is a fact that a subspace of a Hausdorff space is again Hausdorff. Therefore X is also Hausdorff, okay. So X is subspace of Y and subspace of, this is fact that subspace of Hausdorff space is Hausdorff, hence X is Hausdorff. Now to show that X is locally compact, so to show X is locally compact, what we have to show, we have to show that for any point little x in the topological space X, so we have to find some compact subset of X denoted by Cx and some open subset of Ux of X such that X belongs to Ux and Ux contained in Cx. Now For that, we consider any point little x in the topological space X and infinity from the complement of x in Y. Then already we have seen that Y is Hausdorff. Therefore, there exist open subsets U and V, open subsets in Y such that x belongs to U and infinity belongs to V, and their disjoint U intersection with V equal to empty, and V is open of type 2. Therefore, so here we have denoted V open subset of Y containing infinity. So this is V infinity. So then we define Cx equal to Y minus V infinity. Okay, so this is Cx is compact subset of topological space X. Okay, so here Cx is Y minus V infinity, where V infinity and U x they are open disjoint open subsets of Y containing, this contains infinity and Ux contains x. Okay, from Hausdorff property of the topological space Y. Okay, now it is easy to see that these are the required sets. Ux, this is open in X, and Cx compact subset of X. So for these two sets we have X belongs to Ux, okay, and Ux contained in Cx. Therefore X is locally compacted at X, and X is arbitrary point of X. Therefore X is the topological space X is locally compact. Okay, this completes the proof. Okay, so now we have an exercise here. Suppose X is not compact, that is X is topological space locally compact and Hausdorff, but it is not compact, and Y is the topological space constructed in the proof of this theorem, then show that X closure equal to Y. Okay, this is very easy exercise. So basically you have to show that infinity is a limit point of X, that is every open neighborhood containing infinity. Okay, every open neighborhood of infinity in Y intersect X closure. Okay, this is very easy exercise. So basically enough to show that every open set of Y of type 2 intersect X. Okay, now we have the definition of compactification. So if Y is compact Hausdorff space and X is a proper subset of X such that closure of X equal to Y, then Y is called compactification of X. For example, if you take close interval 0 1 as Y equal to close interval 0 1 and X equal to open interval 0 1. So on Y we have subspace topology of Euclidean topology, and so X is subset of Y, so here we have subspace topology of Y. Then one can see that with this topology X closure equal to Y, and y is compact Hausdorff. Okay, y is compact Hausdorff, close interval 0 1 is compact and Hausdorff, and x is subspace of y such that x closer equal to y. So for example, for example, close interval 0 1 is compactification of open interval 0 1. Okay, now in particular if y minus x has only one element, that is the complement of x in y, that is singleton set, then y is called one point compactification. Okay, so here we have exercises show that the one point compactification of the real line is homeomorphic to circle, and the second one is following. In general, show that the one point compactification of the Euclidean space Rn, this is of dimension n, where n is greater than or equal to 1, this is homeomorphic to the sphere Sn of dimension 1. So recall that Sn equal to the set of points in Rn plus 1 with norm equal to 1. So I would insist you please try to solve the exercises.